Welcome to my talk about the approximate evaluation of first-order counting queries. I'm Jan Dreyer, and this is joint work with my supervisor Peter Rosmanit. This work is concerned with algorithmic meta-theorems. Meta-theorems have two components: a logic that is used to describe a class of problems, and a graph class that describes the input. Meta-theorems then state something along the lines of all problems expressible in a certain logic can be solved efficiently on certain graphs. Meta-theorems provide a powerful way to reason about whole families of problems at once. The most famous meta-theorem probably is Cosel's theorem, which states that every problem expressible in monadic second-order logic can be solved in linear time on graph classes with bounded tree width. A second important meta-theorem states that one can solve every problem expressible in first-order logic on sparse graphs. By sparse graphs, we usually mean the notion of bounded expansion and no-way denseness. These are very robust notions that generalize, for example, planar graphs, bounded tree width, or excluded minors. The second meta-theorem holds therefore for more general graph classes than Cosel's theorem, but only for the weaker first-order logic. In general, there's a trade-off between the expressiveness of the logic and the generality of the graph class. In this paper, we extend this meta-theorem for sparse graphs to a more general logic. We analyze the logic FO greater 0, which is a counting extension of first-order logic, and show that one can approximate every problem expressible in this logic on bounded expansion graph classes. To do so, we present the new concept of approximate model-checking. We also show matching hardness results. Our results seem to imply that FO greater 0 is the right logic to capture approximation problems on sparse graphs. I will start my presentation with an introduction to model checking and sparse graph classes. If you want to jump ahead directly to our results, go to the time marker that is printed on the screen. Since our results build on top of first-order logic, let's start by explaining how you can use first-order logic to express problems. Our first example would be independent set. If you want to express whether a graph has an independent set of size k, you can do the following. You write down the first-order formula. There exists vertices x1 to xk, such that all pairs of xi and xj are not adjacent and not equal. You use this tilde symbol here to express adjacency, and you cross it out to express non-adjacency. Another example would be dominating set. A graph has a dominating set of size k if and only if there are vertices x1 to xk, such that all vertices y are dominated, which means y is either adjacent to one of the xi or equal to one of the xi. And in these two examples, you see all the basic operations of first-order logic. You can existentially and universally quantify over vertices. You can ask whether vertices are adjacent or equal, and you have negations and conjunctions and disjunctions. Another use case would be database queries. It turns out that first-order logic can be used to capture some of the basic elements of SQL. But in general graphs, it seems like you cannot solve these problems much faster than the trivial n to the k algorithm. This is why we consider sparse graph classes, where it turns out that you can solve these problems much faster. Instead of coming up with a separate algorithm for all these problems, we want to encode these problems as logical formula and then evaluate the formulas. This evaluation problem is known as a model-checking problem. Formally, it depends on a graph class G and a logic L. The input is a graph from the graph class and a sentence from the logic, and the task is to decide whether the formula is true in the graph or not. Our goal would be to find a linear FPT running time algorithm. This means we want an algorithm with a running time which is some function of the length of the formula times n, where n is the size of the graph. If we're successful, then we can express independent set and k-dominating set using a formula whose length depends only on k, and then evaluate this formula with a running time which is some function of k times n. So for every fixed k, we get a linear time algorithm for k-independent set, k-dominating set, and so forth. Okay, let's next talk about sparse graphs. You're probably all familiar with planar graphs or bounded degree or bounded tree width graphs. Cosel's theorem exactly states that on bounded tree width graphs, the MSO model checking problem is FPT, but we want to consider more general graph classes. There's the concept of topological minor freeness, which generalizes all these three graph classes, and the concept of bounded expansion and nowhere denseness is even more general. There is a result by Grohe, Kreuzer, and Sieberts, which states that first-order model checking is FPT on nowhere dense graph classes. And this is, in a sense, optimal. A graph class is somewhere dense if it is not nowhere dense, and for graph classes which are somewhere dense and closed under taking subgraphs, the first-order model checking becomes as hard as on general graphs. So in this work we focus on bounded expansion, which is slightly weaker than nowhere denseness, but behaves usually in a very similar way. The first idea to characterize sparse graphs would be to require that the ratio of edges to vertices is bounded by some constant for every graph in the graph class. However, this is not restrictive enough. Assume we start with an arbitrary graph and subdivide every edge once, then suddenly the ratio is at most 2. So we need some kind of more restrictive measure. And bounded expansion is defined as follows. We pick some subgraphs of a graph, and each of those subgraphs has radius at most r, and then contract these subgraphs into single vertices. The result is what we call an R-shallow minor. And we require that the ratio of edges to vertices is bounded by some function f of r for every R-shallow minor of every graph in the graph class. This turns out to be a very robust definition with many algorithmic applications. Okay, so with all the basics in place, let's continue with the results of this paper. We develop all our ideas using the partial dominating set problem. The input to this problem is a graph and two numbers k and m, and the task is to decide whether there are k vertices which dominate m vertices. This problem cannot be expressed in first-order logic, since we would need m existential quantifiers, but m is generally assumed to be unbounded. However, on h-minor free graphs or apex minor free graphs, the problem is still solvable in FPT time. You can express partial dominating set in the logic f or greater 0. This logic extends first-order logic with the ability to ask whether there are at least or at most m elements with some properties. And the formula to express partial dominating set looks like this. You see one new operator here, #y, which stands for the number of vertices y which satisfy some property, written in the parentheses. And you can ask whether that's greater or smaller than some number m. And the partial dominating set formula reads as follows. There are k vertices x1 to xk, such that the number of vertices y with the property in the parentheses is greater than m, and in the parentheses is written that y is either adjacent or equal to one of the xi. So there's k vertices such that the number of y which are dominated is greater than m. And the crucial thing now is that the length of this formula depends only on k and not on m. So no matter what value m has, it contributes always a length of 1 to the formula. So we can formally define FO greater 0 as follows. We say that it's built using the normal rules of first-order logic and one additional rule. We can write the number of y that satisfies some formula phi is greater than m, where m is some arbitrary number, and phi can again be an FO greater 0 formula. So we can have some kind of nested counting going on. The first example formula would be the partial dominating set formula that we've seen already. And the second example would be the H index. A scientist has an index of H if it has at least H papers which have been cited at least H times. In FO greater 0, you can express it like this. You say the number of my papers with the property in the parentheses is greater than H. And in the parentheses, we write that the number of other papers which have cited my paper is greater than H. Let's next talk about the algorithmic tractability of the model checking problem for FO greater 0. The good news brought to us by Kuske and Schweikart is that the model checking problem for FO greater 0 is FPT on bounded degree graphs. On the other hand, the bad news is that on almost all other graph classes, the problem seems to be hard. We show hardness of model checking on forests of depth 3 by reduction from k-clique. Assume we're given a graph and we want to decide whether it contains a k-clique. We assume the vertices to be the numbers from 1 to n, and we iterate over them. Here we have a vertex I with neighbors j, k, and l. We insert the following tree into our forest. The root is labeled by I, and this root has a yellow child with I children each, and for each neighbor a blue child. These blue children have n-j, n-k, and l-l children each. And we'll do the same for every neighbor of the original graph. Now two vertices ij of the original graph are adjacent if and only if the corresponding vertices in the forest satisfy the following property. At the one vertex, I pick the yellow child, and at the other vertex, I can pick a blue child, such that the combined number of children of the yellow and blue child is exactly n. This way I can create an f or greater 0 formula, which when evaluated on the forest is true if and only if the original graph contains a k-clique, which means that model checking on such forests is hard. Okay, we now know that exact model checking for f or greater 0 is hard. This is why we do approximate model checking. Let us again use the partial dominating set problem to gain some intuition on what it means to approximately evaluate a formula. Assume we ask whether there are k vertices that dominate m equals to 5,000 vertices. Maybe the answer is no, but for m equals to 4,983, the answer would be yes. Or maybe the answer is yes, but for m equals to 5,017, the answer would be no. In both of those cases, small perturbations in m change whether the formula is satisfied or not. We say that in this case the situation is unstable. We formalize it as follows. Let epsilon be greater 0. A formula phi is said to be epsilon unstable on a graph G if scaling the counting literals of the formula by 1 plus minus epsilon changes whether the formula is true in the graph or not. This now finally brings us to our main result. Let G be a graph class with bounded expansion and epsilon be greater 0. We show that there exists an algorithm which takes a graph from the graph class and an f or greater 0 formula phi and runs in time, which is some function of the length of phi times n, the size of the graph, and the algorithm either returns yes or no or I don't know. If the algorithm returns yes, then we are guaranteed that the formula is true on the graph. If the algorithm returns no, then we're guaranteed that the formula is false. And if the algorithm returns I don't know, we're guaranteed that the formula is epsilon unstable on the graph. So the algorithm is never allowed to return the wrong answer, but it may say I don't know if the formula is unstable. Note that we can achieve an arbitrary accuracy by choosing epsilon as small as we want. So let us now see what this means for the partial dominating set problem. If there exists a set of k vertices that dominates at least 1 plus epsilon times m vertices, then the formula is satisfied. And even increasing m a little bit, the formula still remains satisfied. So it is stable and the algorithm is guaranteed to return yes. On the other hand, if all sets dominate less than 1 minus epsilon times m vertices, then the formula is unsatisfied, and even lowering m a little bit, the formula remains unsatisfied. So it is also epsilon stable on the graph, and the algorithm is guaranteed to return no. The remaining case is the following. All sets dominate less than 1 plus epsilon times m vertices, and there exists a set that dominates at least 1 minus epsilon times m vertices. Only in this case the algorithm is allowed to return I don't know. So even if we get the answer I don't know, we still gain a lot of information. In this setting we find out that the exact answer is somewhere in an epsilon window around m. Also in practical settings, the numbers in the formula may itself be approximation or may have some kind of safety margins built in. So you could imagine that an approximate evaluation is in this case almost as good as an exact evaluation. For the special case of partial dominating set, we actually go one step further in our paper and prove that one can solve the problem exactly in FPT time on bounded expansion graph classes. This even holds for all formulas that consist of an existential block, followed by a counting quantifier, followed by a first order formula. Next, you may ask yourself whether one can extend the expressive power of f or greater 0 while still maintaining its nice algorithmic properties. Here we give a negative answer for many natural extensions of the logic. We show that approximate model checking becomes hard on trees if we allow, for example, the comparison of two counting terms, such as asking whether the number of vertices y with some property is greater than the number of vertices z with some property, or counting tuples, or multiplication of counting terms, or subtraction of counting terms. This hardness of approximation even holds for very large approximation ratios. Note that we see a very sharp drop in hardness from an approximation scheme on bounded expansion to hardness of approximation even on trees. In summary, we show that it's hard to evaluate f or greater 0 formulas even on trees, but it's possible to approximate them on bounded expansion graph classes. On the other hand, slight extensions of f or greater zeros are hard to approximate even on trees. It therefore seems like f or greater 0 is the right logic for approximation on sparse graphs. So the great open question of our work is whether one can extend our approximation model checking scheme from bounded expansion graph classes to no-dense graph classes. In the past, all the algorithmic results for bounded expansion have been later proven to also hold for no-dense graph classes, and we're optimistic that in the case of approximate model checking, this will also turn out to be the case. As the last part of this presentation, I want to sketch how a model checking approximation algorithm works. We do something called quantifier elimination. This means step by step we remove the innermost quantifier of a formula until the formula has no quantifiers left and we can directly evaluate it. Assume we're given this formula in some kind of pre-next normal form. The formula states that the number of x1 with some property is greater than m1, and the property in question is that the number of x2 with some other property is greater than m2, and this property is that the number of x3 that it satisfies some quantifier-free first-order formula dependent on x1, x2, and x3 is greater than m3. In a quantifier elimination procedure, we grab the innermost quantifier-free formula together with the innermost quantifier and replace it with an equivalent quantifier-free first-order formula. The resulting formula has one quantifier less. Again, we grab the innermost quantifier-free formula and innermost quantifier and replace it. So step by step, we eat up the quantifiers until we're left with a quantifier-free first-order formula, which we then can trivially evaluate. Let us now show how a single quantifier elimination step works. To simplify things, let's assume the formula that we want to simplify looks like this. We asked whether the number of x3 that is adjacent to x1 or x2 is greater than m. In other words, we asked whether the union of the neighborhood of x1 and x2 is greater than m. Next, we make a case distinction based on the size of the intersection of the two neighborhoods. At first, let's assume that the size of the intersection is relatively small compared to the union of the neighborhoods. We can write the union of the neighborhoods as follows. We sum over the first neighborhood plus the sum of the second neighborhood, but we have to subtract the intersection because we've counted it twice, so we subtract it here. But since we're only interested in an approximate evaluation of the formula, we can simply ignore it. This simplifies our problem to deciding whether the sum of two neighborhoods has size at least m. Next, we introduce unary predicates. R greater I of x is true if and only if the neighborhood of x has size at least I. Using these predicates, we now build formulas. And the formula we build looks as follows. We make a disjunction over all values of I ranging from 0 to m, and then ask whether x1 has a neighborhood of size at least I, and x2 has a neighborhood of size at least m minus I. The resulting formula is true if and only if the size of the first neighborhood plus the size of the second neighborhood is at least m. But there's one big problem with this formula, and the problem is that the length of it grows with m. We explicitly need a formula whose length is independent of m. And in order to do that, we don't branch or we don't make a disjunction over all possible values of m, but only over the values 0 epsilon m, 1 epsilon m, 2 epsilon m, and so forth. So we divide the numbers between 0 and m into equidistant buckets, and we only try 1 divided by epsilon many numbers between 0 and m. This way the length of the formula is now independent of m. Let me next try to convince you that the formula is still a good approximation of the original formula. Here I've written down all combinations of neighborhood sizes that are accepted by the formula. For example, the first neighborhood may have size at least m, and the second one may have size at least 0 epsilon m, or the first one may have size at least 7 epsilon m, and the second one at least 1 epsilon m, and so forth. Assume now we're given two neighborhoods whose summed size has size at least m. We can align them like this, and since the first one has size at least 6 epsilon m and the second one has size at least 2 epsilon m, this combination of neighborhoods would be accepted by the formula. On the other hand, assume we're given these two neighborhoods whose combined size is clearly less than m. We see that no matter how we align them here, they will not be accepted. So the formula will reject these instances. So far the formula has made no mistakes, but assume now we're given these two neighborhoods whose combined size is just barely larger than m. Then we're in unstable territory, because if we increase m just a little bit, then suddenly the yes instance becomes a no instance. And we notice that in this case the formula may make mistakes, because no matter how we align these two neighborhoods, they will be rejected by the formula. But this is something that we can deal with, because we're allowed to return I don't know if the situation is unstable. Okay, let's now come to the second case. The second case assumes that the neighborhood of x1 and x2 have a relatively large intersection. We will show that this second case does not happen too often, and therefore we can deal with it. Assume for contradiction that we have a fixed x1 and many other neighborhoods have a large intersection with the neighborhood of x1. If that is the case, then you can show that there is a large subdivided clique somewhere in the graph. And this is a contradiction to the assumption that our input graph comes from a graph class with bounded expansion. This means for a fixed x1, there are not too many x2 that have a large neighborhood intersection. And for simplicity, we assume now that there's only a single x2 with a large intersection. And we call this vertex now f of x1. Next, we define a unary predicate qf of x, which is true if and only if the neighborhood of x combined with the neighborhood of f of x has size at least m. And now we can define our final formula. Either x2 is equal to f of x1, and in this case we can simply return qf of x1, or x2 is not equal to f of x1. And this means we're in the first case of the case distinction, where the two vertices have a small intersection of the neighborhoods, and we can simply return the formula that we defined earlier. And this completes the step of the quantifier elimination procedure. We have constructed a quantifier-free formula that approximates the original formula. We can now repeat this process to remove the quantifiers one by one until we're left with a single quantifier-free formula that we can then directly evaluate. And that completes my presentation. Thank you very much for watching, and if you have any kind of feedback or questions, please drop me an email.